Hello and good evening. I'm Bob Lindemeyer and welcome to ISU Media Message. The program, as hopefully you know by now, is designed to present a number of the films and videotapes that have been produced here at Iowa State University to a wider television audience. Normally when these productions are finished, they're used in the classrooms or they're used for very special and specific purposes. And in the past, we haven't had an opportunity for the television audience to see them. Tonight, my guest is Gerald Schwartzbaugh. Jerry is with the Center for Non-Destructive Evaluation here at Iowa State. Jerry, what does that mean in a nutshell?
It's life cycle maintenance of airplanes is what we're talking about, Bob, using techniques not unlike what you see in a hospital for maintaining the human body. It's applied to airplanes to make sure that they are structurally sound throughout their life cycle. Engines and fuselage components primarily.
You can test it without tearing it apart, literally. Huh?
Exactly.
Okay. Now, the video that we're going to see tonight was done for the division that is really sponsored in major part by the Federal Aviation Administration. Did I say that right?
That's exactly right.
Yeah.
It's an internal training effort to educate their own people in an awareness level, I guess you would say, to the various techniques, because their field inspectors come from such a variety of backgrounds. They may well not have been introduced to this technology prior to coming to work for the FAA.
Okay, and the division of the university's program, the Center for Aviation Systems Reliability. Okay, so that's what, applying these techniques we've been talking about.
Exactly.
To the aviation business.
That's right.
Well, good. Let's take a look at this videotape then. Again, produced for the Federal Aviation Agency, and it's called Non-Destructive Inspection for Corrosion Control.
The average age of the world's jet fleet is increasing. So is the average age at which aircraft are retired from service. Today, large numbers of operating aircraft have completed as many as 90,000 takeoffs and landings. The airworthiness of these aging aircraft can be subject to corrosion degradation in the form of stress corrosion cracking and corrosion fatigue. In today's aggressive operational environment, more inspection and better inspection are needed to ensure that our older planes are safe. The FAA is developing guidelines which will limit the amount of corrosion allowed on older aircraft and establish more comprehensive inspection, maintenance, and prevention programs for the airlines. Corrosion is an insidious problem, for not only is it frequently hidden from view, but it can be the precursor to fatigue, weakened structures, and in the case of the aviation industry, the potential for catastrophic impact on public safety. The control of corrosion is based on early detection and repair. Non-destructive inspection techniques are being widely used today to detect the presence of corrosion. For NDI techniques provide a cost-effective approach to early detection and the reduction of repair costs associated with advanced corrosion problems. Non-destructive inspection techniques include X-ray and radiography, with which individual parts or assemblies can be pictured either on or off the aircraft and subsequently analyzed for corrosion, cracks, or flaws. Eddy current, with which a skilled technician can gather and interpret a variety of highly reliable data on aircraft skin thickness, minute cracks or flaws in parts or around rivets and fasteners. Ultrasonics, with which totally hidden cracks and corrosion can be detected in or on an aircraft anywhere that can be reached with the ultrasonic probe. Dye-penetrant and magnetic particle inspection, with which individual parts and components can be reliably analyzed for cracks or flaws. And most importantly, visual inspection. The experienced eye of a skilled inspector can detect that telltale ripple or loose rivet that suggests the presence of corrosion and demands more sophisticated inspection.
Norm Cornell from the FAA.
Glad to meet you, Art.
Yeah. What are we doing here, Norm?
Well, I'm inspecting the lower rudder actuator on the 727.
The FAA inspector is not required to be an expert in non-destructive inspection techniques, but it is important to understand the fundamentals of these NDI procedures. The FAA inspector must employ knowledgeable observation, working cooperatively with the air carrier's maintenance staff, questioning and probing when appropriate to assure the safety of all those who fly. This videotape training program has been designed to provide FAA inspectors and engineers with an overview of NDI techniques for corrosion detection. NDI techniques which currently are in use by commercial operators and independent repair and maintenance facilities in the inspection of civil transport and commuter airlines. In Part 1, following a brief review of corrosion theory, each of the 5 basic NDI techniques will be described. Instrumentation will be introduced and demonstrated. Technique, calibration, and interpretation will be discussed. In Part 2, these current NDI techniques will come to life as they are documented in their real-world application to aircraft maintenance. Additionally, Part 2 will briefly introduce some of the emerging technology and research in the NDI field. The dictionary defines corrosion as the process of being eaten away gradually, especially by chemical action, as in rust. More specifically, corrosion is the destruction of metals by chemical or electrochemical action, and is caused by a reaction between metal parts and aqueous moisture. This process gradually converts the metal into a flaky metallic compound, such as an oxide. An understanding of the types and forms of corrosion in aircraft is essential to the process of using NDI techniques for the detection and control of corrosion. Modern aircraft are constructed of materials selected for their structural efficiency and light weight. Notwithstanding heat treatment and a variety of corrosion protection sealants, treatments, paints, and preventative practices, corrosion does occur. Severity of corrosion varies with aircraft type, design characteristics, and operating environment. Exposure to salt water, exhaust gases, high humidity, condensation, spillage, dirt, and dust all affect the degree of corrosion. Common areas of corrosion potential in aircraft include structures under lavatories and galleys, fuselage belly areas, fuselage skin, particularly in lap joints, structures adjacent to doors. Common types of corrosion found in aircraft include surface corrosion, characterized by a dulling appearance. If allowed to proceed, the surface will become rough and eventually pitted. Here, pitting corrosion is evident on a section of unpainted belly skin. Galvanic or dissimilar metal corrosion can occur between any two metals of different electrical potential. Steel fasteners in aluminum alloy skins are a good example. While paint and plating are applied to reduce the problem, any crack or crevice can admit moisture and foster galvanic corrosion. The hidden nature of crevice galvanic corrosion of fuselage skin is difficult to detect, for the thinning is not visible until it has eaten completely through. Research continues on the insidious correlation between corrosion and stress, which creates stress corrosion cracking. The corrosion may not be obvious. In fact, it may be only an exposure to the corrosive environment that fosters stress corrosion cracking. Hidden, insidious, costly, and life-threatening, corrosion in its various forms and types must be found and controlled. Non-destructive inspection methods and techniques are critical to corrosion detection. While the most obvious and least sophisticated, visual inspection with mirror and flashlight continues to be a very important method of detecting corrosion. The patient and thorough visual search by an experienced inspector is critical to the checks and rechecks that constitute a top maintenance program. Visual inspection procedures include working a small, well-defined section of the aircraft before moving on, taking the time to use your experience and knowledge of those areas prone to corrosion development, and staying alert, looking and feeling for those signs that suggest or demand another look with more sophisticated NDI techniques. Although the majority of this training video is spent on the technology-based NDI techniques, the reality of NDI is that more than half of today's inspections rely on visual methods. Radiography, or literally photography by shortwave radiation, includes more than traditional X-rays. Gamma rays and neutron radiation can also be employed. Fundamentally, the process passes radiation through the sample being inspected, exposing an image on the film, which is then developed and viewed. Although radiography can be done on the aircraft, most of this work is done in an X-ray room to avoid radiation hazards. In this facility, major components such as this elevator can be handled. The inspection requirements and scheduled paperwork accompany the component. The film pack is positioned opposite the X-ray generator by the radiography qualified technician. The radiation hazard alone demands special training and qualifications. Frequently, the X-ray test documentation will call for the use of an image quality indicator. These wire penetrometers function like a photographic step wedge. When placed in the shot, they help to confirm the sensitivity of the image. A final check of alignment, and the technician leaves the chamber and pulls shut the lead-lined door. Exposure energy and time are critical to the specific shot being made. After processing, the dried negative image is retrieved and examined over a light box for the telltale changes in density that would indicate the presence of corrosion. Accurate analysis requires skill and experience. In this negative image of an elevator trim tab, the treacherous-looking anomaly is not a crack, only a bead line of epoxy. A well-exposed radiograph in the hands of an experienced technician can be a highly reliable inspection tool. Eddy current inspection technology and procedures have evolved into a variety of highly reliable NDI detection schemes. In its simplest form, basic eddy current testing involves setting up a calibrated electrical field and then observing and analyzing how that field changes as it passes through materials. The typical eddy current instrument displays a calibrated trace on a CRT and incorporates a variety of probe styles to precisely deliver and receive the eddy current signals. Training, skill, and practice are important, for there are many variables with eddy current technique and calibration. Here the technician is calibrating for a range of skin thickness testing. Virtually every test requires a calibration reference standard made of the exact materials and thickness to be studied. After calibration is established, the probe is applied to the required test. This sample piece of aluminum skin was removed from the fuselage of a jet transport. The exterior surface has already been ground smooth, but the interior reveals an area of severe thickness loss due to corrosion. This split screen demonstrates the sensitivity of low-frequency eddy current technique in the hands of a skilled technician.
First one is the baseline. We got slight material loss. And this one here is approximately 10% material loss. And this one is up off the screen and it gets that high, you really don't know exactly what percent, but you know it's getting pretty bad.
Low-frequency eddy current testing can be used to detect cracks and thinning caused by corrosion in multi-layered structures. High-frequency eddy current tests employ small diameter probes, like this right-angle probe, and can detect small surface cracks and flaws. Special tests use custom probes. For example, here's a bolt hole probe, which is rotated 360 degrees while inserted in the hole and can detect surface corrosion and cracks. Eddy current is one of the most frequently used tests to measure depth of corrosion or corrosion loss. Ultrasonic inspection uses high-frequency sound waves to detect a change in echo or reverberation pattern caused by a flaw. The control unit generates the sound wave and shows the echo return, either by CRT display or digital readout, as seen here. To ensure transfer of sound waves, a gel-like liquid couplant is applied to the test surface. Calibration is required either with a step wedge standard or on a known portion of the actual test area. Echo time correlates to thickness. Basically, the sound pulse travels into the bulk of the material under test until an echo is reflected by the back surface. This CRT display shows good calibration, for the times between echo spikes from the back surface are equal and linear. If the material has been thinned by exfoliation corrosion, this new surface causes echoes to return in a shorter time. Similarly, a stress corrosion crack within the material creates an echo return sooner than the calibrated back surface. Because the smallest crack or separation will affect echo return, the ultrasonic test here detects an otherwise unseen delamination flaw within this alloy skin. The reliability of ultrasonic thickness testing is compromised when the surfaces are not smooth. Pitting and corrosion, even paint, can cause the ultrasound to be scattered and attenuated. Dye penetrant inspection is used with all metals as well as on ceramics, plastics, and glass. The basis of this inspection method is that the dye enters any surface crack or flaw, and after cleaning and processing, that crack or flaw is highly visible. In this example, the pylon bracket being inspected is lowered into the penetrating die bath for a specific period of time. Some manufacturers recommend quality control of the procedure via the use of known test blocks. Next, the part is thoroughly rinsed with a solvent cleaner and water, which removes all surface dye, leaving only that which has penetrated any cracks or pits. After the part is heat dried, it's subjected to the developer, in this case, a fluorescent powder type developer. As shown, gloves and air mask safety precautions are recommended. Under ultraviolet light inspection, the developed dye shows up as a brilliant yellow-green color. The dye penetrant technique will detect surface porosity and fatigue or stress cracking, but it cannot see inside the structure. Because this inspection revealed a crack on the interior surface of a bolt hole, this pylon bracket is tagged for rejection. If the part being inspected is susceptible to magnetism, it can be inspected by the magnetic particle inspection method. The process requires that the part be magnetized. Then, finely divided ferromagnetic particles are applied in dry powdered form or flushed on in a liquid suspension, as in the system demonstrated here. The particles here are also fluorescent and under black light are even more revealing of defects at or near the surface of the part. The startup includes agitation of the mag particle suspension liquid, as well as checking of the particle concentration. Since the system recirculates, particle content can be depleted. The part being inspected, in this case a high-strength steel fuse pin, is magnetized in the high-energy field of the unit and flushed with the mag particle solution. The flux meter confirms the presence and direction of the magnetic lines of force. Then, under black light, the fuse pin is inspected for any disconformity in these lines of force, an obvious indication of a flaw near the surface. In order to locate a defect, it is essential that the force lines pass approximately perpendicular to the flaw. Therefore, it's important to reapply the magnetism at right angles to the initial pass. Following successful testing, the part is demagnetized to avoid the potential of residual flux attracting filings or interfering with navigation gear on the aircraft. No flaws being detected, this part is tagged OK for reinstallation. Although limited to ferromagnetic materials, magnetic particle inspection has proven a highly reliable method of detecting flaws at or near the surface. Non-destructive inspection techniques represent a unique mix of science and skill. The procedures and technology must be carefully and thoroughly disciplined. The FAA inspector, knowledgeable of the manufacturer's and carrier's NDI requirements, plays an important role in assuring the airworthiness of our aging aircraft fleet.
There you have it. Non-destructive inspection for corrosion control, a film produced here at Iowa State for the Federal Aviation Agency. And my guest is Jerry Schwartzbaugh. Jerry, how's the tape being used by the FAA?
It's being used in two ways, one of which is distribution to their various field offices for their people to view at their convenience as a refresher and an introduction. And also it's being incorporated into their formal training program, which is at Oklahoma City, at their training center there.
Used by the inspectors that are charged by the FAA to go out and inspect these airplanes, make sure they're being taken care of. Right?
Exactly.
Okay. Makes it safer for all of us to fly, right?
Exactly right.
I know that the crew and I enjoyed a lot of cooperation from the folks at Northwest Airlines. You might comment on their involvement in this.
Well,
project.
they're extremely interested to make sure that the people that they work with within the FAA, their inspectors, are knowledgeable about what they're doing and what they are doing to ensure airline safety. You'll see that quite frequently in the airline business, that there are a lot of barriers that would otherwise appear in the business that doesn't appear there because of the central focus on the safety of flight aspects.
Right. Jerry, I want to thank you for bringing in the tape and being our guest tonight. We look forward to talking to you again.
It was my pleasure, Bob. Thanks for asking
Good.
me.
You've been watching ISU Media Message. We'll see you here next week.
This and most of the programs seen on the ISU Media Message are available for rent through the Iowa State University Film Video Library. Write to Media Resources Center Film Video Library, 121 Pearson Hall, Iowa State University, Ames, Iowa 50011. Or call 515-294-1540.